Now, we know what a reducible and irreducible representation are. Representations behave like vectors in symmetry space. Now what does it mean? Let's understand this using the three layers. Layer 1. Functions such as px, py, and pz orbitals. These are the real vectors in the real physical space. Then, Layer 2. Matrices, which are operators acting on those vectors and transform them. And finally Layer 3. That is characters of representations, which are vectors in class function space. When we say representations form a vector space, we are mainly talking about Layer 3. A representation assigns a matrix to every symmetry operation. And the dimension of the matrix will depend on the number of bases. If your basis has one function, then matrices are one-dimensional. For two functions, matrices are two-dimensional. For three functions, it is three-dimensional. But in representations, whether it is reducible or irreducible, we do not use the full matrix here. Instead, we compress each matrix to a number, that is the trace of the matrix. This is the character that carries the information of the matrix. So a representation, both reducible and irreducible, contains the characters and is really a set of matrices. It is important to mention that functions are the real physical space. It has a real physical meaning. But representations are abstract form. And each representation becomes a list of numbers. And that list behaves like a vector. We call them vectors because they follow the mathematics behind the vector. Like, they can be linearly added to give a new vector, can be multiplied by a scalar, and can be decomposed to form new vectors, as from reducible to irreducible forms. For example, a reducible representation can be represented as tau is equal to character of E, character of C to character of C3 and so on. This is a vector space. Suppose a point group has 4 classes. So, whether it is reducible or irreducible representation, it will have 4 characters as shown here. To this representation, we can say it is a 4-dimensional vector. Now, here, we should not be confused with the dimension of the functions, which is the character of identity element that we have explained earlier with the dimension of the representation. The dimension of any representation is equal to the number of class present in that point group. To simplify this, let's take the example of C to V. Here, irreducible representation, say A1, will look like this. And B1 will look like this. So, these irreducible representations have 4-dimensional vector space. In molecular symmetry, the irreducible vectors are considered as the basis vectors. A basis vector is one set of independent vector needed to build every other vector in a space. And a basis vector cannot be further reduced, like the irreducible representations. Now, we have another 3-layer picture. Layer 1 is the individual representation, which is called a vector space. That can be reducible or irreducible representation. Layer 2 is a direct sum of irreducible representation, builds larger spaces that we called reducible representations. And Layer 3, a larger vector space, such as reducible representation can be reduced to smaller vector space that we will call basis vector or irreducible representation. So, a reducible representation is the larger vector space. And it can contain multiple irreducible representations which are the basis vectors. This can be represented as tau is equal to tau1, plus tau 2 plus tau 3. Next, we will discuss what is the physical meaning of addition, that is tau is equal to tau 1 plus tau 2 plus tau 3. Multiplication. And what is transition moment integral?